Welcome to ilectureonline. In this video, we're going to explore what an integral is or what integration is. An integral is really the opposite of a derivative. Therefore, we sometimes call it an antiderivative. Integration, that's the term of actually doing the process of doing an integral, is the opposite of differentiation. So let's go back and see what differentiation is, and then we'll figure out what the opposite of differentiation is, and then we should be able to understand what an integral and what integration is. Let's start with the equation y equals x squared minus 4x plus 3, a simple quadratic equation. If we were to graph it, it looks just like this. It goes to the y-axis at x equals 3, it goes to the x-axis at x equals 1, and at x equals 3. So there's two real roots here. If we now take the derivative of that function, we call that dy dx. The derivative of y with respect to x, we also call it y prime. And the way we do that is we take the exponent from the x variable right here, place it in front, and subtract 1 from the exponent. So 2 minus 1 is 1, so we get 2x to the first power. Same here, we take the exponent, we multiply times the minus 4, so we get minus 4 times 1 times x to the 0 power, and of course anything to the 0 power is simply 1, so we simply get minus 4. And the derivative of constant, since this is x to the 0 power, we put the 0 in front, 0 times anything is 0, the constant just disappears. So this is what we call the derivative of the original function y equals x squared minus 4x plus 3. Now what does that derivative mean? And especially since it still has the variable x in it. Well, what the derivative is, in this particular case, it's the slope for any value of the function x. Now, if I plug in a value, for example, I want to know what the slope of my function is when x equals 0. That's right here. So you can see that's a fairly big negative slope. We plug in 0 for x. 2 times 0 minus 4. That 0 minus 4 gives us minus 4, which means the slope here is minus 4. If you want to know what the slope is at x equals 1, 2 times 1 minus 4, that's minus 2. So at 1 here, the slope is minus 2. If you want to know what the slope is at x equals 2, 2 times 2 is 4, 4 minus 4 is 0. The slope here is 0, and that looks like it's apparent here. The slope here is 0. And finally, if you want to know what the slope is at x equals 3, 2 times 3 is 6. 6 minus 4 is a positive 2. So at x equals 3, you can see that we have a positive plus 2 slope. Now let's say that we start with the derivative. Y prime equals 2x minus 4. How do we get back to the original function? If someone says, here's the derivative of a function, I want you to find the function, well, what you need to do to go backwards, that's the opposite of differentiation, is you need to integrate. You need to find the integral of that. So to go from y prime, which is the derivative, back to the original function, we need to do an integration. The symbol for that is as follows. We could then say that y is the integral of y prime. Oh, I should say put in an equal sign there. So it's basically, now that's not the exact right notation, but we use that little s symbol there. That means integration. We're going to integrate y prime. More properly written, we write it like this. Y is equal to the integral of this derivative right here, which is 2x minus 4, and then we write times dx. Remember, whenever we take a derivative, we have that dx here. So we put the dx and put it back over here. We write as 2x minus 4 times dx. So we get dy. So y prime or dy goes in here. And to find y, we take the integral of that. Now, how do we take the integral of that? Well, we do the differentiation in reverse. What we do is we add 1 to the exponent. So this is equal to 2x to the 1 plus 1. It had the 1 exponent there. We add 1 to the exponent, and we divide by the new exponent. So 1 plus 1, which is actually 2, but I just want to show you what that means. So we write 2x to the 1 exponent more, or 1 more to the exponent, divided by the new exponent, minus 4. Remember, this was 4x to the 0 power. We're going to add 1 to the exponent and divide by the new exponent, which is 1. And then we have to add what we call a constant of integration. We just call it c. C stands for constant, and we'll see just in a moment what that means and why we do that. It's kind of a mess. Let's simplify and see what that looks like. So this is equal to 2x squared divided by 2 minus 4x to the first power plus some constant, or, let me come over here, we can say that y is equal to x squared minus 4x plus some constant. and that is the integral. We go back and got the original function back. Let's say, well, wait a minute. The original function had a 3 there, and you have a c there for a constant, so any arbitrary constant. And the reason for that is that once we take the derivative of a function, if there's a constant there, we lose all information about the constant. It just disappears because the derivative of a constant is 0, and so we get this back, which means we don't know what the constant was in the first place. And no matter what the constant is, the derivative will always be the exact same value. Let me show you. Let's say we had another function. Let's say we had the function y is equal to x squared minus 4x plus 8. If we now take the derivative, y prime is equal to 2x minus 4. Again, the constant drops out. Notice that the derivative for this function is exactly the same as the derivative of this function. So when we take the integral, which means the derivative, the opposite to the derivative, the antiderivative, we come back, we get the first two terms, but we don't know what the third term was. We don't know what the constant was, so we just put a symbol in there. There's some constant there, we just don't know what it was. And so to find out what that constant is, we need to have some more information about the function to figure it out. And we'll show you how to do that later. But now at least, I hope we have an understanding what an integral is and what integration is. In other words, if we take a function and we find the derivative of the function, which basically is finding the slope of the function, then to go take the derivative and get back to the original function, we integrate it. We find the integral of that derivative to get the function back. And that's what we mean by integration. It's at least one of the concepts of integration. There's other concepts, and so we'll show you some more videos to get you familiar with what some of these other concepts of integration is. But this is the basic concept of integration. This is how you know that you can go back and forth from a function to the derivative, from derivative back to the function. However, of course, that's not the whole story. So if you want to know more about integration and integrals, stay tuned and we'll show you some more videos. In this video, we're going to try to gain a little bit of understanding of what an integral is and what integration is. Here we have a function written on this graph where we have a relationship between time and velocity. The function is written as v as a function of time is equal to 5 times t. Notice that after 1 second, if this is a driver standing in front of the red light, the light turns green, the driver pushes on the gas and the car accelerates. You can see that after 1 second, the car is moving at 5 meters per second. After 2 seconds, it's moving at 10 meters per second. After 3 seconds, it's moving at 15 meters per second, and so forth. So the equation v of t is equal to 5 times t represents the velocity of the car as a function of time. All we have to do is plug in a value for t, and we get the velocity. If t is equal to 0, we get 0. If t is equal to 1, we get 5. If t is equal to 2, we get 10, and so forth. So the equation tells us how fast the car is moving. What do we get when we take the derivative of the function? The ddt of v of t is the rate of change of the function. In this case, the rate of change of the velocity. So what is dv dt or v prime? It is the acceleration. The rate of change of the velocity is the acceleration. So in this case, the derivative represents the acceleration of the motion. The function v of t represents velocity. The derivative of velocity represents acceleration. Now the question is, what does the integral of the function represent? The integral of the function, and we'll see that later, really represents the area underneath this curve. And the area underneath this curve represents how far the vehicle has traveled. So in this case, the integral of a function that's called the velocity of some object, if we take the integral of that, we actually get the distance traveled. So this is equal to the distance traveled. Now, let's go ahead and take the derivative, or in this case, let's take the integral of that function. The integral, that would be the integral of the function, which is 5 times t, 5 times t dt. And again, we have to have this dt there because that came from the derivative. This is equal to 5 times t, add 1 to the exponent, which is now a 2 instead of a 1, divided by the new exponent. So therefore we can say that this is equal to 5 over 2 t squared, and it represents the distance traveled. If we plug in 0 for t, we get 0. If we put in 1 for t, we get 2.5 meters. If we plug in a 2 for t, we get 10 meters. If we plug in 3, 3 squared is 9 times 5 is 45 divided by 2, which is 22.5 meters. So this equation now represents how far the car travels. The original function tells us how fast it's traveling, and we take the derivative function, tells us how fast it's accelerating. So you can see that integration tells us information about the function. It allows us to go from the derivative back to the original function, or starting from the original function, we take the integral of that function. It tells us something else about the function. In this case, it tells us how far the car has traveled. So there's all kinds of examples like that, and we'll show you some more to get a better feel of what integration is. So again, the methodology of integration is simply, in this case, for a simple function like this, we add one exponent, we add 1 to the exponent and divide by the new exponent. So in this case, instead of t, we get t to the second power divided by 2, and of course then we get 5 over 2t squared, which then in this case represents how far the car has traveled. And that's how it's done. Here's another way in which we can look at integration and integrals. In this case, we're going to deal with the definite integral, and I'll show you in just a moment what we mean by that. Here we have a graph that represents the acceleration of an object. Notice that when time is equal to 0, the object is already accelerating at 5 meters per second. So let me go ahead and put the number 5 there. You can see that as time goes by, the acceleration increases over time. And after 5 seconds, based upon the equation right here, we can see the acceleration as a function of time is equal to 0.5 times t plus 5. So it starts out when time is equal to 0, the acceleration is 5 meters per second, and for each second it increases by 0.5 meters per second. And I should say per second square, of course, because that's acceleration per second squared. So after 5 seconds, let's say this could be a car, would then be accelerating at 7.5 meters per second square. Now, what we can do here is we can find what the velocity would be after a certain amount of time by realizing that the velocity is the integral of the acceleration. Another way of looking at it, the integral of the acceleration will be the area underneath this graph. So this area right here represents the velocity of the car as time goes by, assuming that when time is equal to 0, the initial velocity was equal to 0. So the question is, what will be the velocity of the car after 5 seconds? So for that, we're going to take the integral, and then later on we're going to check our answer by calculating the area underneath this curve to show that they should indeed be equal to each other. So velocity is equal to the integral of the acceleration, and since the acceleration is equal to this equation, we can say that it's the integral of 0.5 times t plus 5 times dt. We always have to have the dt there because it's the opposite of the derivative, and the derivative, that's where the dt comes from. And we'll see later on how that works. Also, this is going to be what we call a definite integral because we're going to evaluate that integral from a starting point to a finishing point. We start at t equals 0, and then we end up at t is equal to 5. So the limits of our integrations, we call them, is from t equals 0 to t equals 5. That's how we can evaluate the velocity after 5 seconds. That's what we're trying to find. We're trying to find the velocity after 5 seconds. We take the integral of the acceleration function and we evaluate it between those two values. We'll show in just a moment how to do that. First, the integral. Again, v is equal to, let's add 1 to the exponent, 0.5 times t squared. Set it to the first power, it's now to the second power, divided by the new exponent, plus 5 times t to the first power, because we had t to the 0 power there before, so now we have 5t to the first power. And normally we would add a constant of integration, but since we have limits there, the constant of integration will disappear by itself. We'll show you later how to do that, but here we can simply say when we have a definite integral with limits on the integral, we can just put the numbers there like this, and we do not have to put in a constant of integration. How do you evaluate the result here? What this means is that we want to plug in the upper limit, 5 for the value t, and subtract when we plug in the lower limit. Let me show you what that looks like. So the velocity after 5 seconds is equal to 0.5, that's a 0, 0.5 times, we plug in the upper limit, that would be 5 squared, divided by 2, and this is indeed a 2, plus 5 times 5. So what we did here is we plug in the upper limit. Each case we see a t, And then we subtract from that when we plug in the lower limit. Of course, you can see when I plug in the 0 there, I get 0.5 times 0 squared divided by 2 plus 5 times 0. And of course, that simply disappears because 0 times anything is 0. And this would then be the result of our integral. V is equal to 5 squared is 25 divided by 2 divided by 2, that's divided by 4. 25 divided by 4 would be 6.25 plus 5 times 5 is 25, so that's for a total of 31.25. After 5 seconds, the car should be moving at 31.25 meters per second. So the units would be meters per second for velocity. All right, let's see if we got that correct. Let's go back over here and evaluate the area of this graph right here. We can divide this into two regions. We have a rectangle. That rectangle is 5 by 5, so that's 5 high and 5 wide. So 5 times 5, that's equal to 25. That's the area of this portion. And now we need to add the area of the triangle. Triangle, notice that it has a height of 2.5, a height in this direction of 5, and so the area of a triangle is 1/2 the base times the height, 1/2 the base, which is 5, times the height, which is 2.5, so that would be 2.5, that's 12.5, divided by 2 is 6.25, so that's the area of this portion of the graph. If we add those two together, notice 25 plus 6.25 does indeed add up to 31.25, which shows that if we take the function, in this case the acceleration is a function of time, and we take the integral of that function, we get the velocity. And then if we want to know what the velocity is, after 5 seconds, we plug in the limits of integration, as we call them. We put in the upper limit here, we put in the lower limit there. When we take the integral, we add 1 to the exponent on every variable, so this is 0.5 t squared divided by the new exponent plus 5 times t to the first power divided by 1, and then we put in the limits. When we plug in the upper limit, we get 31.25. When we plug in the lower limit, we get 0. And so this tells us that after 5 seconds, the car is moving at 31.25 meters per second. And as we said before, the integral of a function like this is equal to the area underneath the curve. When we calculate the area of the rectangle and the area of the triangle, we add it together, we get the exact same value, showing that in essence, when you take the integral of a function, you're finding the area underneath this curve. And depending upon what the function is, that area will have a particular meaning. In the case of the function being an acceleration, the area underneath an acceleration curve is equal to the velocity of that object. And that's why the area here equals the velocity of the object after 5 seconds. So there's another way of looking at integration. Integration tells us something about the function. In this case, if the function is acceleration, it tells us the velocity. And there's many more examples where the acceleration has some meaning. And once you figure out how to do the acceleration, then you can find the meanings in those functions by doing that acceleration. And that's what we mean by integrating and integration. In this example, hopefully we'll get again additional information, additional understanding of what an integral and what integration is. Again, we're going to do a definite integral. Here's a function. This function describes the velocity of an object as a function of time. Velocity is equal to 2t squared. T is in seconds, velocity is in meters per second. And assuming that we start at velocity equal to 0 when time is equal to 0, what is the velocity after 5 seconds? And what is the integral of that function? When we integrate v of t, what do we get? And it turns out the integral of a velocity function is the distance traveled. Let's say that's equal to x. So therefore, we're going to find x when we take the integral of the velocity function. And in this case, we want to find out how far the object traveled after 5 seconds. So we plug in the limits of integration from time equals 0 to time equals 5 seconds. That makes it a definite integral because we're going to evaluate the integral for specific values of t. So when we integrate that, we get the following. X is equal to the integral. The function in this case is 2t squared. We still need the dt from the differentiation from time equals 0 to time equals 5. Now again, we understand that the integral of a function is represented by the area underneath this curve. But in this case, the area underneath the curve is going to be very difficult to figure out geometrically because we have this curve here and it's very difficult to figure out the area. But that's why integration is so handy. With integrals, it doesn't matter what the function looks like, we can always find the integral. So let's go ahead and find the integral of this function. X is equal to, when we integrate this, we get 2t to the third power. We add 1 to the exponent, divide by the new exponent. We do not need to add a constant of integration if we have limits. If it's a definite integral, we don't need to add the plus c. And we're going to evaluate it from time equals 0 to time equals 5 seconds, which means we're going to plug in the upper limit for t and then subtract when we plug in the lower limit. That's going to look as follows. This is equal to 2/3 times 5 cubed, when we plug in the upper limit, minus 2/3 times 0 cubed when we plug in the lower limit. And of course, 0 cubed is 0, so we don't need that portion. That simply drops off. So it's 2/3 of 5 cubed. That means that the distance traveled is equal to 2/3 times 125, because that's what 5 cubed is equal to. And that's 250 divided by 3. 60, let me get a calculator out. 250 divided by 3 is, 250 divided by 3 equals 83.3. That's what it was. Meters. That's the total distance traveled after 5 seconds has elapsed, which is, by the way, equal to the area underneath this curve. That would be difficult to figure out. But again, when it comes to understanding what an integral is, in this case, if we have a function that represents velocity, we then understand that if we take the integral of that function, which means finding the area underneath this curve, and want to find out what the area in the curve means between 0 and 5 seconds. In this case, the area underneath the velocity curve means distance traveled. And if we then take the integral of the function, which means add 1 to the exponent divided by the new exponent, and then evaluate it from the starting point, time equals 0, to the end point, time equals 5 seconds, we plug in those limiting values, we then get the distance traveled through that. So integration, if in the case of having a velocity function, means we're trying to find the distance traveled. In the previous example, we saw that if we have an acceleration function, the integral of an acceleration function is the velocity, and in this case, the integration of a velocity is equal to the distance traveled. Simply just another example of what integrals are, what they can be used for, and why we need them. And there's plenty more examples like that, where when we take the integral of a function, we get a specific meaning, and that's what it's all about. In this case, we're dealing with kinematics, and so the integral of an acceleration function is velocity, the integral of a velocity function is distance traveled. And that's what we mean by integration and integrals. In previous videos, we established that integration is in a way finding the area underneath a curve. If we take, for example, the integral of the function f of x, that is equal to the area underneath the curve graphically represented by that function f of x, so it would be equal to the area underneath this curve. So to get a feel for what integration is, let's think about it this way. If I'm trying to find the area underneath the curve, and of course because of the curve it's difficult to do, I can approximate the area by drawing rectangles on the graph. I can go here, draw a line straight up to this line, then draw a horizontal line here and say this is the area A1 of this section right here, which approximates the area underneath the curve. Now you say, well, approximates, is not about twice the area, and I would agree, yes, it's quite a bit more, but let's say that it's at least somewhere in the ballpark. I can do the same with this second section right here and draw a line this way, and I can say that this is area 2 and that this area of the rectangle is a little bit more than the area underneath the curve. And I can go ahead and do that again for this section right here, and close enough. There we go, and you can say that this is area 3, which is again approximately the area underneath the curve, and I can do area 4, which again I can say is approximately equal to the area underneath the curve. A little bit more, but hey, we're close, we're in the ballpark. I can say then that the area is approximately equal to the sum of all the areas, and in this case there's 4 sections, so from I equals 1 to 4. Of course, most people would say that's quite unsatisfactory because I do think I have quite a bit more area than should be underneath the curve. Well, what I can do to remedy that is I can have more sections, make them thinner like that, and do the same thing. So I can come up here and say this is the area 1, and do this here, this is area 2, and here this is area 3, and this is area 4, and this is area 5. And I come up here, this is area 6. This here is area 7. This here is area 8 and area 9, and this is area 10. Now you can see that if I add up those 10 areas from 1 all the way up to area 10, you can see that there's not as much that pokes up above the curve right here. So if I add up all these additional areas here, those are definitely smaller than the total of these 4 right here. And so I can say that when I sum these up, the area is approximately equal to the sum from I equals 1 to 10, because now I have 10 sections of all the A sub i's. Again, you may say, well, that's true. It's not quite as bad, but it's still not nearly as good as I would like it. What you can do is, again, have more sections like that. In this case, I have 32 sections. I had 4 here, I have 10 here. Here I have 32 sections. And when I do the same thing here, notice that now the area of these curves right here very closely resemble the true nature of this graph and the total area underneath this curve. If I just keep doing that, you can see that yes, I do have slightly higher or slightly more area than I should have, but you can see now that the excess area that I have in those small little triangles above the graph, they're not really that much when you add them all up. When you go all the way up to here and eventually you get the last area right here, this would be the area of the last section right there. You can see that when you add them all up, the area underneath the curve will be approximately equal to the sum of all the A sub i's, in this case I going from 1 to 32. I think you begin to see the pattern. If I just want the area in those rectangles to exactly equal the area underneath the curve, I just need to come up with more and more and more rectangles. 32 isn't enough. Maybe I need 100. Maybe I need 1,000. How about if I have 1,000,000 rectangles? They're all so thin that the excess area, that little corner that would stick out, is so minuscule in size that at that time, for all intent and purposes, if I add up 1,000,000 of those rectangles, the area underneath included in those rectangles would be very, very, very closely to the area underneath the curve. In essence, when we go to an infinite number of areas, if I let the number of areas go up to 1,000,000,000, 1,000,000,000,000, 1,000,000,000,000, then in the end, as it goes to infinity, the area added up for each of the rectangles will exactly equal the area underneath the curve. And it turns out that's in a way the definition of the integral. The integral of the function f of x dx going from 0, in this case from 0 to 4, because we have a definite integral, we only want to do it underneath this region of the function, in essence is equal to the sum, or I should say not like this, but I should say the limit as the number, so we go from I to 4, or from I to 10, or from I to 32. If we call this number n, and the limit where n goes to infinity of the sum from I equals 1 to n of all the A sub i's. So with other words, if we just make enough rectangles, millions of them, billions of them, so they're so thin that the additional area sticking out is so minuscule small, then in essence, if I go to the limit where I let n go to infinity, an infinite number of rectangles, the area summed up by all those rectangles will exactly equal the area underneath the curve, and in essence that is equal to the definition of this integral right here. So integration is basically find the area of the curve by making the rectangles thinner and thinner and thinner. In the limit, when the thickness goes to 0 and the number goes to infinity, all the areas added together will exactly equal the integral of the function. And that's another way of looking at integration and looking at integrals. In the previous video, we saw that the concept of integration is finding the area underneath a curve, and we can approximate that by snipping the area underneath the curve into rectangles and calculating what the area is of the rectangles and say that's approximately equal to the area underneath the curve. To illustrate that, we're going to do an example. So here's the function f of x equals x squared plus 2. We have the horizontal axis x, the vertical axis y. We're trying to find the area underneath this curve, and we're going to do it by approximating this. We're going to draw 4 rectangles. The first rectangle will have a height equal to this. The second rectangle will have a height equal to this, the third rectangle, and then the fourth rectangle. And this is area 1, this is area 2, this is area 3, and this is area 4. Now, let's call this, so x equals 4 is at the end here. Let's say that this is x1, x2, x3, and x4. x1 is equal to 1, x2 is equal to 2, x3 is equal to 3, and x4 is equal to 4. The width of each of the rectangles, let's just call that a delta x. So the width here is a delta x, the width here is a delta x, and delta x. How about the height of each rectangle? Well, the height here will be the function evaluated at x1. The height here will be the function evaluated at x2. Over here, the height will be the function evaluated at x3. And here, it will be the function evaluated at x4. So that's the height of each rectangle. F at x1, f evaluated at x2, f evaluated at x3, and f evaluated at x4. Now, the total area will simply be equal to A1 plus A2 plus A3 plus A4. So that would be equal to the area of the first rectangle, which is the width, delta x, times the height, which is the function evaluated at x sub 1, plus the width of the second one, delta x, multiplied times the function evaluated at x sub 2, plus the width, delta x, times the function evaluated at x sub 3, and the width of the fourth rectangle multiplied times the function evaluated at x sub 4. In each case, those represents the height of each of the rectangles. I can factor out a delta x, so this is equal to a delta x times the function evaluated at x sub 1 plus the function evaluated at x sub 2 plus the function evaluated at x sub 3 plus the function evaluated at x sub 4. What is delta x equal to? Well, delta x will be equal to the total width divided by the number of rectangles. In this case, we can say that delta x will be equal to 4 divided by 4, there's 4 rectangles, which is equal to 1. And of course, by inspection, we can see that's the case. What about the height in each case? What is f of x sub 1? F of x sub 1 is the function evaluated at x sub 1, and x sub 1 is equal to 1. So f, when x is equal to 1, is equal to, that would be 1 squared plus 2, which is equal to 3. Function evaluated at x equals 2 is equal to 2 squared plus 2, which is equal to 6. The function evaluated at x equals 3, that's equal to 3 squared plus 2, which is equal to 11. And finally, the function evaluated at 4, x equals 4, is equal to 4 squared plus 2, which is equal to 18. Those would be the heights of the 4 rectangles. And we also now know the width, so let's go ahead and plug that in. So this is equal to 1 times the height of the first rectangle, which is 3, plus the height of the second rectangle, which is 6, plus the height of the third rectangle, 11, plus the height of the fourth rectangle, 18. Finally, when we add all those together, 3 plus 6 is 9, plus 11 is 20, plus 18 is 38. So that's equal to 38. Area total of all the 4 rectangles equals 38, which is approximately equal to the area underneath the curve. I'm sure it's lower than that, it's less than that, but it's fairly good approximation. How can we improve upon that? Well, there's 2 ways. One way would be to go ahead and have more rectangles. 8, 12, 16, 20, 100, 1,000. And again, in the limit, as the number of rectangles goes to infinity, that area will be exactly equal to the area underneath the curve. And again, by definition, when the number of rectangles goes to infinity, that's the same as taking the integral of that function. Let's go ahead and do that and see what we get. So we're going to check that answer. The area is equal to the integral of the function times dx, and again, the limits of integration is from 0 to 4. So from 0 to 4, which is equal to the integral of, the function is x squared plus 2 times dx, integrate from 0 to 4. When we integrate that, we get the following. This is equal to x to the third power divided by 3. Remember, we add 1 to the exponent, divide by the new exponent, plus 2x to the first power, because we went from 2x to the 0 power to 2x to the first power, divided by 1, so we just leave that there. And the whole thing evaluated from 0 to 4. Plug in the upper limit, we get 4 cubed divided by 3 plus 2 times 4. And then when we plug in the lower limit, we get nothing but zeros, because when we plug in 0, we get 0. So it would be 0 cubed divided by 3 plus 2 times 0. And of course, that simply disappears. And the actual area, by using integration, notice we get 64 divided by 3 plus 8. 64 divided by 3 is 21 1/3 plus 8. That's 21 1/3 plus 8, which is equal to 29 1/3. That is the actual area you need to curve using integration. Notice the approximated area, 38, isn't that far off, but probably a little bit further than most people would like. In the next video, we actually have a better method to find an approximated value. Again, these techniques are very helpful to understand what integrals are. So let's go ahead and do our next example, the next video, and then you can see how we eventually just always converge to, if you want the actual area, simply take the integral of the function, evaluate it from the two limits, from the left limit to the right limit, or the lower limit to the upper limit, and you get the exact value of the area. And that's how it's done. And here's our next example of how to find, or at least in this case, approximate the area you need to curve. We know that we can find the exact area by finding the integral, but this approximation again shows you how the integral is conceived. And initially, the concept of the integral is really conceived by this particular process. Here we have a curve, y is equal to f of x, and let's say that that curve is equal to x squared plus 2. It's the same curve that we had on the previous example, but we're going to solve this differently. Here, the height of the rectangle is going to be found by drawing a line at the middle of the rectangle to the top, like here. Would be in the middle, and then coming across over here, and now let's call that y sub 1. That would be the height of the first rectangle, not the height determined by the line on the right side of the rectangle. Notice when we do that, and we draw a line across, we have some additional area on the left side, but we have less area on the right side. That means that those two kind of average out, and so the excess area, or maybe slightly less than the area required to find the total area, will be very, very small. So the delta between the approximate area and the actual area will be much smaller with this particular technique. Again, for the second rectangle, we find the height by going down the middle where we hit the curve. This will be the y2, that will be the height of the second rectangle. Notice that, again, we'll have some excess area on the left, but not quite enough area on the right side of the rectangle. We do that again with the third rectangle. This will be the height of the third rectangle, y sub 3. Again, when we draw the rectangle, notice that we have some excess over here, but some lacking over there. And finally, find the height of the fourth rectangle. We come up here. This will be the height of the fourth rectangle, y sub 4. When we draw the rectangle like this, notice we have some excess here, but a little bit lacking there, and they should almost cancel one another out. Again, if we call this a sub 1, call this a sub 2, call this a sub 3, and a sub 4, so this would be the first rectangle, like this. This would be the second rectangle, the third rectangle, and the fourth rectangle. We can then say that the total area is simply the sum of a1 plus a2 plus a3 and plus a4. The width of each rectangle, let's call it delta x again. So this is the width, let's call it delta x. And there again, that would be, the width is delta x. And since the total width here is 4, and there's 4 rectangles, we can say that delta x is equal to the total width divided by the number of rectangles, which is equal to 1. We now just have to find the values for x1, x2, x3, and x4. You can see here that x1 should be equal to 0.5, x2 will be equal to 1.5, x3 will be equal to 2.5, and x4 will be equal to 3.5. Sometimes it's just easier to write as a fraction, so this would be 1/2, 3/2, 5/2, and 7/2. All right, let's go ahead and find the areas now. Area total will be equal to the area of the first rectangle, which is delta x, times y sub 1 plus delta x times y sub 2 plus delta x times y sub 3 plus delta x times y sub 4. And again, we can factor out a delta x here, so we can write that the total area will be equal to delta x, the width of each rectangle, they're all the same width, multiplied times the sum of all the heights of all the 4 rectangles. That would be 3 here plus y sub 4. Now, how do we find the height of each rectangle? We find them by plugging the x values into our equation right here, which means that f evaluated at x equals 1/2 is equal to 1/2 squared plus 2. 1/2 squared is 1/4. That would be 2 1/4. The function evaluated at 3/2 is equal to 3/2 squared plus 2. That would be 9/4 plus 2. 9/4 plus 2. 9/4 plus 2, which is 8/4. That would be 17/4. And this can be written as 9/4. Sometimes it's just simply easier to write it as a fraction. The function evaluated at 5/2 is equal to 5/2 squared plus 2. That would be 25/4. Plus 8, that would be equal to 33/4. And finally, the function evaluated at 7/2 is equal to 7/2 squared plus 2, which is equal to 49/4, plus 8, that would be 57/4. Quickly checking to make sure I did this correctly. 25 plus 8, 33, 49 plus 8, 57, 9 plus 8, 17, and 1 plus 8 is 9. Okay, that is correct. Now let's plug in the values to see what we get. The total area is equal to 1 times y1 is 9/4 plus 17/4 plus 33/4 and plus 57/4. Adding those together, that would be 90, that's 107, plus 9, that would be 116 divided by 4. 4 goes into 125 times, plus 4, that would be 29 times. So the total area, as approximated by this method, is 29. Now let's go ahead and use the integration again. We can say that the exact area is equal to the integral of the function of x times dx, evaluated from the left limit to the right limit, or the lower limit to the upper limit, which is from 0 to 4. That would be the integral of the function, which we said was x squared plus 2 times dx from 0 to 4. If we integrate this, again, remember we add 1 to the exponent, divide by the new exponent. This is equal to x cubed over 3 plus 2x to the first power over 1, evaluated from 0 to 4. Plug in the lower limits. You plug in 0 for x's, you get 0, so we only need to plug in the upper limit. This is equal to 4 cubed divided by 3 plus 2 times 4. 4 cubed is 64. That's 64 divided by 3 plus 8. 64 divided by 3, that's 21 1/3. That's equal to 21 1/3 plus 8, which is equal to 29 1/3. Notice that is the exact area, and this is the approximated area. The approximate area is not a bad way to find the area, and so you can see that they're very close to one another. If you use this method where you pick the height of the rectangle to be the middle where the curve hits the x value when evaluated, when the function evaluated that x value hits the curve right there, if you make the rectangles that particular height, you have a much better approximation, which means you don't need nearly as many rectangles to get the exact value for the area. But again, the definition of an integral is you keep adding more and more rectangles until the number goes to infinity, until the thickness, the delta x, goes to 0, and then you have the exact area, which is equal to the integral, and that represents the area underneath the curve. That's how it's done. And now let's put it all together. We saw some examples in the last several videos where we made rectangles, and we add up the areas of all the rectangles, we got the exact area, or in some cases the approximated area of the curve underneath the function. Of course, the closeness of the area, the approximated area versus the exact area, depended upon what method we used and how many rectangles we had. Here we're going to find the essence of what we mean by integration and integrals. Again, remember, the integral of a function equals the area underneath the curve in that graph. What we're going to do here is find a small little rectangle. So I'm going to draw a rectangle on this graph. Here it is. There's my rectangle. And the rectangle has a small amount of area. We're going to call that small amount of area a dA, like a small change in area, a very small, minuscule amount of area. And that area is equal to the height of the rectangle times the width of the rectangle. And the width of the rectangle is going to be a very small amount of dx, a very small change in x. A puny, tiny little change. So that's a very narrow little rectangle. And the height will be the function evaluated at this particular value for x. So whatever this value for x is, I plug that value into my function, and I evaluate it, I get an f of x, and that will be the height of the rectangle, which is equal to the y. The y is the height of this rectangle. It's the function evaluated for that particular value for x. Therefore, the area of the rectangle is equal to the height, y, times the width, which is a dx. Now, I can do the same for the little strip right next to it. There's another area, and there's another area, and there's another area, and there's another area. And then in the end, if I add up all those areas, if I slice this all into little strips, and I add up all the areas of all those strips, that should equal the area of the total of the area underneath the curve. However, again, you say, well, wait a minute. If you come up here and you look at that, you can see that the area of each rectangle is not exactly equal to the area underneath the curve at that particular location. You have a little of an excess area. And remember that to solve that problem, we just need to make the width of each rectangle a little thinner. The thinner we make the rectangles, the less area you have sticking out there in that one corner. And in the limit, if we just make the thickness of the rectangles thin enough, where delta x goes to 0, where the thickness goes to 0, then eventually if I add up an infinite number of rectangles, that should add up to exactly equal to the area underneath the curve. And by definition, the integral of the function of x times dx, evaluated from the lower limit, let's say from 0, all the way up to the upper limit, 4, equals the area underneath the curve. In other words, when we go to the limit, when delta x goes to 0, that is equal to this. So this is equal, the area is equal to the sum of all the areas of all the little rectangles from I equals 1 to infinity. When we do that, and of course, we can't say that it's equal to infinity, the area is equal to the limit as n goes to infinity, and if we replace that by n, so if I have n number of rectangles, and there's almost an infinite number of them, if n approaches infinity, all those sums of all those rectangles added together will add up to the exact area underneath the curve. And so to find the exact area of the curve, this is equal to the integral of the function, which is x squared plus 2. Remember that the function, which is equal to y, is indeed, in this case, x squared plus 2. So that's the height of each rectangle at each value for x. We multiply that times the dx, which is the width of each rectangle, and that's where that dx came from. If you always wondered, why does he keep putting a dx there? It's because it represents the width of each of the rectangles. We evaluate from x equals 0 to x equals 4, and then if we integrate that, we get x cubed over 3 plus 2 times x. Remember, you always add 1 to the exponent, divide by the new exponent. Here we have 2x to the 0. That becomes 2x to the 1 divided by 1. And then we evaluate that from the lower limit to the upper limit. It means we plug in the upper value. This is equal to 4 cubed divided by 3 plus 2 times 4. So we replace x by the upper limit, and then we subtract from that. When we plug in the lower limit, which is 0 cubed divided by 3 plus 2 times 0. Of course, we didn't need to do that because we could see that when we plug in 0 for lower limit, it just goes to 0. So this simply disappears, and that is equal to 64 divided by 3 plus 8. 64 divided by 3 is equal to 21 and a third plus 8. So eventually we could say that's 29 and a third is the total area underneath that curve. Again, I used the exact same equation I did in the previous examples, but now you can see, in other words, this is what we mean by integration. Integration for functions means we find the area underneath the curve, and depending upon what the function represents, the area underneath the curve will represent certain things, and that we'll see plenty of examples of that. So then we add up all the little strips, all the little areas of each rectangle. The rectangles, we make them thinner and thinner and thinner. The total sum of the area of the rectangles will come closer and closer to the actual area of the total area underneath the curve. And eventually then, when we let the number of rectangles go to infinity, like we do here, that will then equal the integral of the function evaluated from 0 to 4. And that's what we mean by integration. That really is the essence of the concept of integration. And that's how it's done. In this example, we're going to see how integration can be used for many different things. Here we have what we call a circular cone. The radius of the base is 5, the height is 10, and we're trying to find the volume of that cone. Integration is perfect for that task, and let me show you how that works. Now this is just a simple example. There's a limitless number of examples that can be used, that we can use integration for. Here's just one. How do we find the volume of a cone like this? What we're going to do is we're going to take a small little slice of that cone. By doing that, we're going to imagine the tiny little slice with a very tiny thickness like this. If you can see that, that's simply a little slice like that. Here is the radius of the slice, and that would be in the direction of the y-axis, so we're going to call the radius here y. And y is going to be determined where that slice is. If the slice is at the base, we know that it's 5 units long. If the slice is at the very top, we know it's 0 units long. So there's some relationship between z and y, and we'll figure that out in just a moment. But to find the volume of that little slice, we're going to call that volume a small little dv. A small little change in the volume, a tiny little amount of volume. And of course, the thinner we make the slice, the less volume we have there. Of course, the volume of a slice like that would be the area times the thickness. The area would be given by pi times y squared. That's the area of a circle. Now we multiply that times the thickness, and it's a small little distance in the z direction. So we're going to call that small little thickness, we're going to call that a small little dz, a small little change in z. dz like this. To find the whole volume, what we're going to do is we're going to add up all those little slices. We're going to have an infinite number, not quite an infinite, but almost an infinite number of little slices. And when we add the volume of each slice together, we get the volume of the entire cone. Kind of like the way we did it for the area underneath a curve. We take a small little slice, we make another one, we add them all up, and we get the total area underneath the curve. Here we take a small slice and another one, and another one, another one. We add them all up, and that gives us the total volume of the cone. Integration tells us that the volume is going to be the integral of all the dv's. Remember that integral sign? That really means a sum of all the little slices, or the sum, in this case, all those slices in the cone. That means that this is equal to the integral of pi times y squared times dz. Now, since pi is a constant, it can come outside the integral sign, so this is equal to pi times the integral of y squared times dz. Now we have one problem here. We cannot yet integrate this because the variable y is not the same as the variable z. So we have to find a way to express y in terms of z. So we'll go back to the edge of this cone right here, and that looks like a straight line. That reminds us of the equation y equals mx plus b. But in this case, the vertical axis is z, and the horizontal axis is y. So we'll write this as z is equal to my plus b. Now all we have to do is find m and find b, and now we have a relationship between z and y. We can then replace z, or in this case, y by z, and then we can go ahead and integrate that. B is what we call the z-intercept, and that happens at 10. So we can say that z is equal to m times y plus 10. Now we still need to find the slope, and the slope is by definition the rise over the run. In this case, it's a negative slope, and the rise would be a negative 10, the run is 5, so that means z is equal to minus 10 over 5y plus 10, and simplifying that, z is equal to minus 2y plus 10 is the equation that relates y to z via the edge of the cone. Since we need y squared, we need to solve this for y. Moving this to the other side, we get 2y is equal to, move this across, 10 minus z, because the z becomes negative. Divide both sides by 2, we get y is equal to 5 minus 1/2 z. And if we take this and substitute that in for here, we now have only the variable z in our integration sign. We can write this is equal to pi times the integral of 5 minus 1/2 z, quantity squared, times dz. Now we just have to multiply that out. This is equal to pi times the integral of 25. 5 times this times 2, that would be minus 5z, and this squared would be plus 1/4 z squared. Put parentheses around that, times dz. Quick check, we have 25, we have 1/4 z squared. 5 times this is 5/2 z, times 2 is 5z, and it's a negative. All right, now we can go ahead and integrate that. This is equal to pi times, and what are the limits of integration? Since we're integrating over the variable z, the cone goes from z equal to 0 to z equals 10. So our limits are going to be z equals 0 to z equals 10, and we'll plug that at the end. So when we integrate this, we get 25z minus 5z, add 1 to the exponent, divide by the new exponent, plus 1/4 z, add 1 to the exponent, divided by the new exponent, and evaluated from 0 to 10. Now all we have to do is plug in the limits. When we plug in the lower limit, we get 0, so we don't need to bother with the lower limit. We'll plug in the upper limit. Let me come over here, because I'm out of room. So we can say that the volume is equal to pi times 25 times 10 minus 5 times 10 squared over 2 and plus 1 over 12. That would be 10 cubed, like this. Simplifying this just a little bit more, v is equal to pi times 250 minus, that would be 500 divided by 2, that would be minus 250. That's interesting, that cancels out. And finally we get plus 1000 divided by 12. And then times pi with a calculator. Let's find out what that's equal to. 1000 divided by 12, and then times pi equals, and we get 261.8. So the volume equals 261.8, whatever the units are. That could be centimeters or inches, it doesn't really matter. So that's how we do that. Now, this is simply for illustration purposes. This whole section here on what is an integral first showed you what an integral is by definition, what we can do with integrals, how we usually find it to find the area near a curve, but it has many more uses such as this, where we can find the volume of any object, in this case the volume of what we call circular cone. And in this case, again, the principle of integration is that it's a summation of small little things. We slice it up in a very thin little slice where dz goes to the limit, where dz becomes nearly 0. We have almost an infinite number of slices, add them all up, that's what integration is, and it gives us the volume of the cone. Exactly. It's an amazing thing. So there you go. There you have a nice little set of videos that show you what integration is and what you can do with integration. If you're interested, we'll have many, many more videos explaining how we use integration in various settings, because that's really the difficult part, is how to actually go through that process when the equations become quite complicated. But we have lots and lots of examples so that you can slowly get to mastery of how to do the various types of integration. And that's what we mean by integration.